In terms of charge transport, we are more interested about electrons and how do they behave when they are in the sea of uh, atoms, nucleus, positive charges, of course, the nucleus is positively charged. So what are their properties? One thing we saw last time that they have quantized energy associated to them. So which means every electron would have very specific energy. For example, if I'm just throwing number, maybe 3 electron volt, but then another electron would be maybe 6 electron volt. Then probably nothing which will have 3.5 electron volt or 4 electron volt, right? So it's like every electron belongs to very specific energy state. So when we do that, and then we say, okay, you keep on pumping energy to it, but the radiation belongs to a certain energy level, so you cannot have a continuous spectrum, which means that we need a special kind of treatment. So quantum mechanics is what helps us explain those atomic phenomena very well, and it tells us how electrons would behave. Now, some history that we will study because ultimately it leads to what our understanding is today. So Bohr's model, we all have studied Bohr's model in high school as well. So here our approach will be more in line with that. How do we ultimately get to a point where we understand electrons and how they relate to different energy levels? So so Neil Bohr's a scientist. So he started with the concept which is planetary system, right? So planets in galaxies. So how do so they are going around sun, but there is special consideration here where they are in orbits and they do not fall into, and they are continuously being attracted by the nucleus, but they do not lose energy and they do not come out of the orbit and ultimately strike the nucleus. So they stay in the what do you call orbits. So hence he gave a few uh, postulates, a few assumptions, which help us explain why or how they would have different energy levels. And there's simple calculation. Now, the first uh, thing about it is that if you were to use the classical way, how do you do that? The system would break down, right? So, which is that all these things that electrons would lose energy and they would fall down. But the postulates give us a few extra conditions, right? So those conditions are that they have certain stable orbits, and if they are in their orbits, they are not giving off any radiation. They are not giving off any energy. We're talking about a stable system where you haven't introduced any external energy, where we are not pumping out any external energy, right? But we'll see that for devices, we do have to pump energy. So then what happens there? But just simple assumptions postulate to explain that behavior. And then they say that they can change different energy levels, go from lower energy to high energy level. But that would happen either by a cost that we have to get energy from somewhere, or we have to release energy to make up for the difference of high energy level to lower energy level. And this is what was a way to explain what you call the photoelectric effect, right? So the Planck's experiment that we talked about last time. So that difference of energy, now we previously talked E equals hv, right? E equals Planck's constant times the frequency, energy. But now we're talking about the difference of energy. So that difference of energy is related to the wavelength of that that photon that comes out, right? So don't get confused. It's just context. When we talk about the photon itself, it has an energy. For that photon, energy is hv, right? H times frequency. But that energy is nothing but the difference of two energy levels. Remember last time we were seeing that atomic spectra, and we looked at their different energy levels, and we saw that there was an associative additive uh, property to them, that you could add two levels and you would get third level, or within a big level you had two different levels. So now when you look at the orbits to which those electrons belong, the difference of those two orbits would be the same. What is the energy of that photon that's coming out? Understand the idea here? So don't get confused that we were talking about E equals HV and now we are writing E2 minus E1 equals HV. Understand the point here? So when we talk just E, we're talking about the photon. Now we're talking about the difference of the energy between those two photons. Now, another important thing is when things are moving, we have an idea of what we call momentum, right? So when things have certain velocity, they would, if they have mass, they would have momentum, right? If they don't have mass, they don't have momentum. But here, we have talked about particles having wave and mass both at the same time, which means that they have special properties. They are interchanging between mass and so we have to know both of those properties. When we talk about mass, then the mass could be measured, the momentum. Momentum could be measured by a relationship, which is an integer times h. We will see where does that integer come from. But because it's going around, so it has an angular momentum instead of just a momentum, which would be in the straight line. So when you have angular momentum, then we would define it as P naught. We just write P for momentum, but we write not, sorry, it's not P naught, it's P sub angle, theta, right? So P theta would be N times H, where N is an integer. So what does that mean? That different electrons may have different momentum, different angular momentum, right? So higher energy, higher momentum. Makes sense, right? If you have I don't know, if I have a small Toyota Corolla and you have a big truck and you are going at the same speed, which one has more momentum?
The lighter one.
Which has more momentum, the lighter one or the heavier one? If I'm driving a car and you are driving a truck, who has more momentum?
The heavy one.
Omar, who has more momentum? The bigger one, the higher mass, right? But the problem here is the mass of electron is not changing. What is changing?
Its velocity,
It's
acceleration.
so velocity, they are all moving at the same velocity. So it's the energy of an electron. Now think about it. We are taking the classical momentum concept, which is P equals mv, right? Mass times velocity. But the mass stays the same. Velocity stays the same. How does momentum change then? So that's because of n. So the orbit number would define how the momentum would change, right? So do you understand why? So we are talking about quantum mechanics here. We're talking about the properties which are different. So Bohr's model has these special ad hoc relationship, the special relationship to explain the data. And the data was that Planck's constant, the black body experiment, where the atomic spectra of wavelengths showed specific energy level, quantization. So this explains quantization here, that this relationship just tells us that we have some integral number multiple that would help us understand what is the angular momentum. Now, If we take a stable system where an electron is rotating around a nucleus, there is a force from the nucleus that's attracting it towards itself, and then there's centripetal force, which is trying to break it away. So those forces have to be equal for it to be stable, which is this relationship given here. But the understanding of this relationship, that why we equate, that's the most important thing. There is an electrostatic force, charge, which is pulling it, and then there is a momentum-based force. So you see on the left-hand side is Q, on the right-hand side is M. They both have to be equal. Only then the system stays stable. Now, we take this relationship and we apply a few plug and play here and there. We say, okay, the potential energy and kinetic energy, a particle would have both of them. We sum that up, that will give us total energy of a particle in one orbit, right? So, but our problem here is not just one orbit. Our problem here is, okay, what happens when an electron jumps from one orbit to the other orbit? So we need to find the difference of energy. So that's what is shown in 2-16. You probably, this is a very fundamental relationship. So it's important to know that what does it mean. So these are basically bringing both properties, charge and mass, into this. When you do this, we get a relationship that tells us how much is the difference of energy. If you know energy, we can find frequency, right? E equals hv, which we know already. So that's what happened in 2-17. So we have done, it's nothing but applying E equals hv here. Let me write that up. So now you have energy, you divide by h. When you divide by h, you get rid of, you add this extra h here, right? And what is h bar? What is h bar? Does somebody remember what is h bar? We know h is Planck's constant, so it is h over 2 pi. Some basic things, and we are just building on top of those basic concepts. All right. So now, when we have established this, we have a way of finding exactly how much is the energy and what is the difference of energy. Now, if you go back, this whole thing was done for a simple atom, hydrogen. So the Bohr model was for a simple system, one electron, right? So, but essentially now we see the systems that we have, they are more complex. They are not just one electron, they are multiple electrons, right? Especially when you talk about solid or semiconductor materials. That, and we see another thing, that energy levels are not one discrete level. There is slightly differences on the energy levels, even in first orbit, what we call as small splitting of energy levels. I have to emphasize the terminology that I'm using, it's important you understand it now, because we'll be developing the rest on top of that, right? Now, the way it shows, there is a discrete energy. It says, right, exact. We have mass, we have charge, we have on the right hand side, if I look at it, we have very discrete values. So which should mean exact numbers. But the reality is that there are slight variations on the energy, what we call as splitting of band. Let's see in the next slide. So, and it will become clear later on. So eventually what happened is we had to develop slightly more involved theory, which would take care of uh, those anomalies where there are multiple subbands at one band. So we're talking about now just first orbital, but suborbitals, which would have energy slightly up or down from that energy level. Also, we have to now treat more complex materials than just hydrogen. But the concept that electrons have quantized energy state and there is transition between wave and particle, that is established with this theory, what you call Bohr's model. So this is where we get into more complex ideas of quantum theory. Now, there are a couple of things we have to establish and understand before. Probability first. Let's recap probability. We all know probability, right? You have dealt with some probability in mathematics, right? So what is the simple example for probability? Flip of a coin. Take a quarter. If I flip it, what is the probability that I will get a head? Ricardo, what is the probability that I will get a head if I flip a coin?
50%.
50%, one half, right? What is the probability I will get a tail? 50%. What is the total sum of probabilities of all the possible events? What is the total of all the probabilities?
50.
No, all the probabilities. So there's 50% or one half to have head. There's one half to have a tail. So if I want to add the probabilities of all the events, that's half plus half. Total is always one, right? So total of all the possible probabilities is always one. Now I take a step back and I say, okay, we flip two coins. What is the probability that we will get two heads? That's
25%.
25%. Fantastic. One fourth, right? One quarter. What is the so we take any event on these two coins, we'll see it's one quarter. So the total of all the probability is always going to be one, right? Two heads, two tails, one head, one tail, one tail, one head. There are four chances. So the probabilities total sum is always going to be one. Now, why am I building up on probability? Because the problem here is that electrons are moving so fast, we cannot say exactly when an electron is at what location. That's one thing. Number two, the energy of that one particle at any given time is not clear. So there is always going to be difference in energy with respect to certain time. Now, how do we understand that? So there are a few things which we need to know, that it's impossible for us to tell exactly what is the condition of an individual particle at the atomic scale. We know it is there, we know it's moving with certain energy, but we cannot pinpoint exactly where it is and exactly what is its energy level. So what we have to do is we have to find average. It's like you come to school, the class starts at 2, someday you come at 1:55, someday you come at 1:58, some days you get there at 2:02. And if I ask you what time did you get to the class this semester, you give an average number, right? You say 2 p.m. We don't, it's not easy to even keep track of our attendance exactly. And now we're talking about gazillions of electrons, right, which are continuously in motion. So we take the average value, we take the expected value. expected value of position, expected momentum, and expected energy of a particle. When you say expected, then we have to define probability. And when you say probability, here there is a special case where there is always going to be some uncertainty about the position, momentum, and energy of a particle. And that uncertainty is measured. We have a way of knowing the maximum of how much would be, the minimum of that uncertainty. So this is called Heisenberg uncertainty principle. And if you have seen certain show few years ago, Heisenberg, this was his real contribution, not that one. So what Heisenberg was a physicist and he was a quantum mechanics scientist, not cooking stuff. Now, when we talk about uncertainty principle, there are a couple of things we need to know. One is that atomic events, we would always explain those in terms of probability. But the thing is that even then you have to measure the probability. So Heisenberg principle explains that the first one, the simultaneous measurement of position and momentum, which is velocity basically, right, of energy and time is inaccurate to some degree. In a similar way, it says that in the measuring of the energy and at any exact time is also inherently, there is some inaccuracy in that. Now you can look at in another way how it is called the principle of indeterminacy, that we cannot exactly determine where it is. Now, if we establish that there is limitation in the simultaneous measurement of position and momentum, we can then figure out a probability function to do that, to help us there, right? Now, one can say this H Planck. What was the value of Planck's constant? Anybody remembers? You want to look up in the book, what was the value of Planck's constant? It's given on page 62. It's
like
so
5.6 to 10 to the negative 34.
exactly. So it's 6.63
Oh, there we go.
times 10 to the power minus 34. So and it's joules second. It's a very small number. But when you talk about such a small quantity like an electron, and you are talking about gazillions of them, so it becomes pretty significant, right? So the problem we are facing is we cannot exactly determine the position, we cannot exactly determine momentum. So hence we have to define a probability function. And probability function, we call it probability density function, because here what we are talking about is trying to find either we are talking about energy, either momentum. So P is just, we are taking a P as a variable, where we can plug in energy instead of P, we can plug in position instead of P. But we define a probability function Px. We start with one dimension, right? That's easy to deal with. Now, what we are doing here is we are trying to find the particle in an environment and expectation value of these quantities like position, momentum, and energy, right? So expectation value. Now, this one-dimensional function just tells us that there is a possibility of finding it somewhere. So this function, when we have the value, exact value, that will, okay, don't worry, we will not calculate the value, but we just have to know, because what will build up on top of that will make sense, that we know the energy and then we know the probability function that helps us identify the how many charge carriers would be there, right? So that's where it will ultimately lead us. So when we talk about probability, we can plug the values, we can find the values of position, momentum, and energy using this function. Now, this is, we're talking about electrons in a 3D space. And this is just one dimension. So there is a slightly, another thing we have to do, which is that we, instead of finding it somewhere, we take an average of where we can find it. So we take average of the density function. So don't get scared. If you understand what is the probability density function, then you have to know the next step is that we take the average of that density function. So we write the average with this corner brackets. What are these called? Somebody knows what are these called, the corner brackets? Anybody has a better word for these? I call them corner brackets because they're like cornerish type of thing. So we essentially what we have done is we have taken the average. But now the average value can be number across a bigger range. So to make it simplify, we say we take the normalized version of that. So normalization is we divide it with the whole value, and what we get it is probably a normalized probability density function. So if we have to sum up, what we have done is that we have taken the properties of a particle. What are the three important properties of a particle? Position, energy, and momentum, right? And we cannot precisely find those values. So we said the reason is because there's going to be a problem in measurement, and that uncertainty is there. So to take care of that uncertainty, we say we define a probability density function, and that density function is what we use to find average, and we normalize the average value. All right. So it's important concept what we have talked in probability density function, because we'll build up on top of that.